Hello, my name is Chandra, and here I will present the result of my senior mechanical lab experiment, which consists of three modules for three topics, which are heat transfer, thermodynamic, and fluid mechanics. This presentation will be divided into five chapters. The first is about the preparation. It is about the plan of design, shipping, and purchasing components. And then the assembly on experiment. It is about module reviews, working principle, setup, and data collection. And then we move to discuss about the experimental result and analysis, and move to the conclusion, something that I learned from this experiment and the class activity. Also, the last is talking about feedback and suggestion to this class. So without further ado, let's get started. So the setup plan for this experiment consists of three different setups for each topic. They are heat transfer, thermodynamic, and fluid mechanics. My team don't combine the topic into one setup experiment because we think that it is simpler to be analyzed and observed since in one experiment like this, we focus only on one topic. For example, in the heat transfer, we only focus on how the velocity affects the process in convection, and in the thermodynamic, we focus only on the pressure and temperature relation. So we focus only one particular topic, so it's kind of easy to be observed and analyzed. However, one of the drawbacks of this kind of setup is that it's not effective at all, since we must make three different setup for each topic, and it's kind of taking time to do that, so it's not too effective. And then for the shipping plan, it is one go shipping plans, means that one member need to complete all the experiment first and then send it to the other member. Why we do this is because there are several components that will be used for different experiments, so we cannot separate the experiment. For example, like the thermocouple or thermometer will be used for heat transfer, thermodynamic, and fluid mechanics, so we can divide it the separate experiment. We need to one member should complete all the experiment first and then send the setup to the other member. For the purchasing of the component, we decided to book it through online and offline store. For the online store, we booked the component that we cannot find it in the store around our neighborhood, so we book it online. And for the component that can be found easily in the store around our neighborhood, we book it offline. The consideration to book for online store is that we choose the most economical one in the online store with the positive reviews from the other buyers to make sure that the store is really trusted and the component is really working well from the reviews. We see that from the reviews, and we also consider the cost. For the offline store, it is cost and time saving because no need to spend time surveying the store, the trusted one store with a good review on low price. No need to pay the shipping cost and wait for the component to come, and thus it is saving time and budget for the offline store. And here are the list of the online store that we book. Okay, now we are moving to the assembly and experiment. The first one, we will talk about the heat transfer experiment setup. The setup of heat transfer is actually quite easy. It consists of a fan and then a wind tunnel that made of paperboard. In here I use carton paper, and then a mini electric heater inside those wind tunnel, and a specimen that will be heated by this mini electric heater. So well, basically the function of this wind tunnel is that we want to scope the air flows from the fan to be directly hit the steel specimen, and then place the thermocouple into different location on top surface of the steel specimen, and an anemometer to measure the airflows. Okay, so the concept that will be proven in this experiment is how the velocity affects the process of convection. It used the principle of Newton's law of cooling about the temperature rate of change, and Well, basically just imagine that you have a hot coffee and you want to cool off your coffee. You will blow your coffee to cool it off, and notice that the faster you blow your coffee, the faster your coffee to be cooled off. And this phenomena is the topic that will be proven in this experiment. The data collected from this experiment is the initial and final temperature at two different locations on top of the surface of the hot specimen and the velocity of wind from the fan. For the thermodynamic experiment setup, it consists of a box. Well, basically in here we use plastic box because we think that plastic is the bad conductor. Means that it will be prevent the heat to comes out to flows out from inside the box to outside the box, and then place the mini electric heater inside those boxes. It function to heat up the temperature inside the box and will be measured by the thermocouple there, and a syringe to substitute the percent of pressure gauge. Since pressure gauge is really needs a big pressure to move up, so we substitute it using syringe. And when the heat is heated added to the inside the box, the pressure must be increased, right? And it will be pushed up the syringe to move upward, and we will place a plate that will be filled by a flower, so we can calculate the pressure from the moving up of this syringe by the mass from the flower and the plate. The concept that will be analyzed in the thermodynamic experiment is the principle of the ideal gas equation, PV and RT. And from this equation, we can see that P is proportional to T, where the P increase, T should be increases too. And it is animated by this one particular. The pressure law states that for a constant volume of a gas in sealed container or insulated container, the temperature is directly proportional to its pressure. This can be easily understood by looking at this visualization particle moving on a container with a great energy when temperature increases. It is true because when the temperature is increases inside those box, the air molecule inside those box will move faster and they will be bumped to each other and hit the surface uh, inside the boxes, and they create a pressure inside the boxes. The faster they move, the higher the pressure they generate. And if the boxes is really well insulated, those molecules cannot coming out from the boxes, right? And the only path they can coming out from the boxes is from the syringe. So that's why when the temperature increase, the pressure will increase and it will be push the syringe to move up. Okay, so now we are moving to the fluid mechanic experiment. It consists of a box and an enemy in electric heater inside the boxes to increase the temperature of the box, and then a thermocouple to measure the temperature, and a flow meter. It's almost the same as thermodynamic, but in here we use flow meter instead of syringe to measure the airflow's velocity and see how the airflows will behave, whether it will move from the higher temperature to low temperature or vice versa. In this fluid mechanic experiment, the concept that will be used is the principle of fluid flows behavior and volumetric flow rate that is defined as the volumes that flow in a specific range of time, dv over dt, which is equal to velocity times the cross-section area. This equation shows the relationship of area and velocity, where the area increases, velocity should decreases by assuming the volumetric flow rate is constant. See this animation in here, where the bigger area have a slow velocity and the smaller area have the faster velocity. The data will be collected from this experiment is temperature inside the box and the surrounding of the box, so we can measure the pressure and compare it those pressure inside and outside the box, and then flow speed from the flow meter, and inlet area from the flow meter as well. So the experiment you can see on this link, on the YouTube link. You can click it. I will attach it in the description of this video. And here are some documentation of the experiment. Next, we move to the result and discussion. So this is the result of experiment heat transfer. In here, I conduct the experiment with two different velocity, velocity 1 and 2. I do it that way because the fan that I have is the old fan and its efficiency is not as good as a normal fan. In my fan, it can only generate two different speed, lower speed and higher speed. The button of my fan is already broke and left only one button functioning, so that button will be turn on the fan, and then when you push it again it will be generate lower speed, and push it again it will be generate higher speed, and push it again it will turn off the fan. So that's why I can only experiment with two different speed. I think this is one of the drawbacks that I have in this experiment. Okay, so in here I measure the temperature of the ambient air for experiment 1 and experiment 2 with two different kind of velocity. Velocity 1 is slower than velocity 2. And T1 and T2. T1 is temperature on the surface located near the fan, and T2 located far from the fan. And notice in here the result for experiment 1 and experiment 2 rate of change temperature. Apparently experiment 1 has a lower rate of temperature change than experiment 2. And for temperature near the fan, it also have a smaller rate of temperature change than the one that located far from the fan. Why is that way? And here the result, the faster air velocity result in the higher temperature change. Yep, we can see from the previous slide, and the temperature equation is final temperature minus initial temperature over interval over time. And from this temperature change, we can get to know or calculate the heat added or loss from the system. Means that a higher rate of change in temperature, there's also higher heat added or loss from the system. Okay, so this boundary layer, velocity boundary layer and thermal boundary layer, I think it's explained why the temperature 1 in here and temperature 2 far from the fan. So imagine this is the fan. Here is the fan where the air is coming from, and T1 is near the fan and T2 far from the fan. This is why T1 have the lower velocity of airflows than the T2, because the velocity boundary layer is growing as the X is moving further from the leading edge from this. And also similarly for the temperature, where temperature in T1 location 1 is lower than at location 2 is because the thermal boundary layer is also looking like this. It grows as the with x. It grows with x as it go further from the leading edge. So this is a little animation for the convection by the airflows. You can see in here, well, basically convection is about the flowing of the heats, so until you reach a steady thermal distribution. And here there are technical error and human error, where it's come from thermocouple accuracy. I see that thermocouple that I use has an error because in the first place I measured the thermocouple to measure the temperature of ambient air, and they measure different value. One thermocouple measure about 29 degrees Celsius and the other thermocouple only measure 27 degrees Celsius. Obviously, there is an error in the thermocouple accuracy. And for the wind tunnel efficiency also, I think it's not effective, it's not so good in scoping the airflows, because maybe the wind tunnel, the air from the fan can escape from this wind tunnel. And then to measure the initial temperature, it's it's hard to get the uniform initial temperature for each experiment 1 and 2, and also the air velocity measurement also might be have some bias, since I measure the air velocity in the different location, and we can see in here that different locations generate different air velocity. Okay, so this is thermodynamic experiment result. In here, I can measure only the temperature, initial final temperature of the ambient and inside the box, but I cannot get the pressure value, because to get the pressure value, I need the syringe to moving up, because when the syringe is moving up, it will lift the plate that I will be placed above the syringe and filled with the flour, and I will be calculate the pressure from the force causing by this plate and the floor. It is gravity forces, so I can calculate forces over a cross-section area, and I can get the pressure. But since the syringe not moving at all, so I can get this data. So why is become that way? Yeah, apparently there's no movement in the syringe until the experiment done. But I still got some unique fact from this experiment. They are is that firstly, when the temperature inside the box reach 80 degrees Celsius, the smoke start to come out from the box. Means that the insulation start to burns out. Yep, there's the sounds of the insulation burning as well. And when the temperature inside the box reaches 152.2 degrees Celsius, the temperature inside the box cannot increase anymore. Instead, it's decreasing. So I think it could be the highest or the peak temperature that this method of insulation using Korean glue can maintain. Yep, I think the insulation not work so well. So the leakage occurred. It's proven by the smoke coming out from the boxes and the increase of temperature around the boxes. It increased from 30.3 degrees Celsius to 33 degrees Celsius. Also, the pressure inside the box might be really small, thus it cannot move the syringe. And the last fact is that the syringe is melted, thus there's no path for the airflow to flow out. Looking this, the syringe bed is melted, so the air scanners come into the syringe and cannot moving up this plumber here. So I think that's why there's no movement in the syringe. Since syringe is made of plastic and plastic melting point is low, so that's why it's also melting. And here is the fluid mechanic experiment. In here, the result that I can get is only the temperature. While the main point in here is the velocity, but I can get the data for the velocity because there's no movement in the flow meter. And why is there no movement in the flow meter? I think is that because the box is not fully insulated. The insulation is not work so well. So in here, I insulate the box using plasticine, and this plasticine apparently can maintain the temperature inside the box about 180 degrees Celsius. So after reaching this temperature, the temperature inside the box start to decrease. And plasticine start to melt at 100 degrees Celsius, because when reaching this, I can see that the plasticine there is boiled. And then yep, leakage occurred. You can see from the melting of the insulation and increasing of the temperature around the box. It's from 29.8 degrees Celsius to 31 degrees Celsius. Also, the pressure inside the box might be really small, thus it cannot move the flow meter. Okay, so this is the conclusion that I learned from this experiment and from this class activity. Okay, for the conclusion is that I learned insulating the box is hard and need to be careful. We need to conduct careful research of having a good method of insulation. I believe there's so many method of insulating a plastic box so that heat cannot flows out from the plastic box and to prevent the plastic box to melting. But since the time for this experiment is limited, so my team don't have those privilege to conduct this research on how to have a good insulation. And in this experiment, I also learned that plastic might be a good insulator, but not all plastic have the same melting point. So, for example, the plastic box that used by the member, one of my member that experiment before me, it can only maintain 120 degrees Celsius, and the plastic box is melting, while in my plastic box it can maintain up to 180 degrees Celsius and still melting a little bit. So it's still the plastic have different melting point. I think the experiment is intended to be thought and considered carefully because yeah, insulating the box is hard and time management inside the team is also important. From this class activity, I think it's quite fun and enjoyable since we designed the experiment by ourselves. Um, the point is that we need to carefully plan the experiment and time management in the first place. Yes, it tests our understanding on the material that we have learned in the class, how will look like, for example, heat transfer topic, one of heat transfer topic or one of the thermodynamic topics. So using our creativity, how we relate the material of that class into an experiment, how we design the experiment, so we can test our understanding in here, which experiment setup will match the topic. Okay, so for the feedback and suggestion for me, I think the class is fun. Yep, it tests our creativity to practice our creativities, and we need to design our own experiment. And then it's challenging. Seen in here, we not only think about the module of the experiment, how to set up the experiment, but we also think about the budget of the experiment. We cannot make an expensive experiment, or we cannot make an experiment that just as experiment, but we need to think carefully the budget of the experiment. So we need to be wise and plan the budget really good. And also its design setup. Yep, the module, a working principle, and stuff is in the design setup, so it is challenging. And also choosing components. While if we conduct the experiment from the laboratory, the module maybe already given by us, and we don't need to make the module or the design setup, so we don't have to choosing the components, or since all the component already there in the laboratory. But since this is from home experiment, so we need to choose our own components carefully. We need to think what component is match our design setup. For my suggestion, I think it would be good if in the first place student already given several options, maybe about 3 options of experiment setup plan from the module. So in the first place, we already have 3 options to do the experiment, 3 module setup that already made by the lecturer, and we can choose whether we want to use the setup plan given, or we can creating our own setup plan. I think these 3 options in the first place will help the student to have a first imagination, the first illustration of how the experiment will look like, and they can modify from that given experiment to creating their own setup plan. Yeah, yep, this is the references that I use during the experiment, and that's all. Thank you.